interval of convergence. Oh boy. All right, so this time we've stepped it up a bit. We're now looking for the interval of convergence. So let's start by finding the radius in the center, and then check the endpoints, just like we'd always do. So same as it ever was, we're going to go ahead and do the ratio test to try to decide where this thing is. We don't have to worry about them dare negatives, because we're inside the absolute value part. So we've got our n plus 1 term. I'm going to go ahead and just make that an n plus 4. So we got our x minus 1 to the n plus 1. Okay, so there's our n plus 1 term. Let's throw in our n term to the n. We're going to have a n plus 3 and an x minus 1 to the n. Okay. So some stuff cancels, just like always. 2's going to cancel with that, so we're just going to get a 2. N plus 4. And then, of course, that's going to cancel with that. The x minus 1's are going to cancel. Okay. Just like last time, you can pull out that x minus 1 because it has nothing to do with the n. 2 to the n plus 3, n plus 4. All right, so now you're on the test, you're running out of time. Hopefully you can just look at this and you say, okay, the highest power of n on the top, 1/2. Highest power of n on the bottoms, 1/2. But the co-leading coefficient on the top is 2, whereas on the bottom it's 1. And so you think to yourself, okay, this limit is 2. So x minus 1 times 2. All right. And now, again, the ratio test says that this will converge when it's less than or equal, or less than 1. And so if we divide by 2 on both sides, we get x minus 1 is less than 1/2. So just like every time, let's keep that farther away from that. The formula is x minus a is less than the radius. So where a is the center, so our a here is going to be 1, and the radius is 1/2. So now we know the two endpoints of our intervals are going to be radius is 1/2, center is 1, so 1/2 plus 1, 3/2. 1 minus 1/2 is 1/2. And now we just got to decide what kind of brackets to put around this, right? So it's okay, so I guess I should say we know it converges for x between these two. And now we need to decide if we put little, equal signs there. So we need to check for x equals 1/2 and x equals 3/2. We need to check. So let's plug in x equals 1/2. And what do we get? Just straight into the sum. Negative 2 to the n. If x equals 1/2, 1/2 minus 1 is negative 1/2 to the n, all over square root of n plus 3. So that's going to be the same thing as, these are just going to, 2 times negative 1/2 is just going to be 1. This is the same thing as square root of n plus 3. If you're on the test, you don't have to go through this, but you might compare this to, you're just going to compare this to 1 over n and do the comparison test. But on the test, you don't have to. You can just say it diverges. I'm not going to write out the whole thing. And then, let's see, how much room do I have? I'll go do it over here. Let's plug in. So we know it doesn't converge for 1 half. So let's find out if it converges for 3 halves. And you guys can probably see what's going to happen. We got a negative 2 to the n. And then 3 halves minus 1 is 1 half to the n, all over n plus 3. And this is going to be equal to the 1 half and the negative 2 become just negative 1 to the n, all over n plus 3. And then the alternating series test, because 1 over square root of n plus 3 goes to 0, and because the terms are increasing or decreasing, we know by the limit or by the alternating series test, this converges. Converges. All right. So it didn't work for 1 half, but it did work for 3 halves. And so we know our interval of convergence is not going to include 1 half, but is going to include 3 halves. So I got to put a little thing there. Boop. There we go. And there's your interval of convergence.